LGMCTS, language-guided Monte-Carlo tree search for executable semantic object rearrangement. Everyday tasks such as set up the kitchen involving organizing objects based on verbal instructions, a process that is intuitive for humans, but that presents significant challenges for robots. For example here is I'm asking the UR5E, organize the phones into a line on the table. Once that's sorted, focusing on the bottles located to the left of the cube, it's crucial that we avoid any collisions. These simple examples shows many different challenges here. First is the understanding language task descriptions. Secondly, being able to plan the order of subtasks. Basically, this is the ability for planning, which is essential for the problem we are dealing with here, tabletop rearrangement problem. Third one, making sure the result plan is executable. Here it is like we need to avoid any collisions. Before we go into the method, let's look at the previous method, how they are doing with this problem and what their drawbacks. Traditional solvers such as PDDL, strips, or MCTS. The limitation of these planners are they require a very specific and organized formulation for the initial configuration and goal configuration of the problem. They usually require a very detailed configuration. For example, I want to put the table into a position of 111, 222, or something like that, which is usually not accessible in the language-guided problems, especially for language tasks, because nobody will describe the problem as that. As for the understanding language, people will think about the recent progress of large language models. Models such as GPT and Llama has demonstrated impressive potential in understanding complex scenarios and exhibiting zero-shot planning capabilities. One work is called Large Language Models as Few-Shot Planners. And this work has showed by presenting the large language model with few examples, the large language model can do some sort of planning. However, this setup doesn't solve the challenge 3, which is making sure the resulting plan is executable, because there is no physical constraints for the large language models to generate a plan. So sometimes the plan generated by large language models are not executable. So there comes to a recent formulation where we plus large language models with planners. So there has been some trials trying to incorporating between them, such as large LLM graph and AutoTMP. Yet those methods are not able to handle semantic rearrangement problems due to their straightforward formulation. Some methods only consider pairwise relationship, and some methods only support discrete space representation. So let's talk about our method, LGMCTS. The key insights behind LGMCTS, large language-guided Monte-Carlo tree search, is the goal from nature language is vague. So it usually describes a distribution of a goal instead of a specific goal position. Think about the case. Here I say, I want to put a ball to the right side of the table. So when I'm talking about this, I'm not talking about a specific pose. I'm not talking about a pose like 111, 222, 333. I'm actually talking about a region. And if I put this object to any parts of this region, they all fit my goal. So this is a key observation. Language determines the type and parameters of the goal distribution. And we use MCTS to compute the exact goal and the steps we need to take at the same time. We need to define a key conception here, pattern, for better understanding the following detailed method. So a pattern here is a shape that can be formalized by multiple objects or between objects and spaces. For example, put block A, B, C into a line. So here, block A, B, C are formalizing a line pattern. For example, another example here is put circle A to the right side of block B. So circle A and block B formalize a spatial pattern. So when we are using language to describe a rearrangement goal, this goal can be decomposed into multiple or one patterns. So I can put A, B, C into a line, and at the same time, I can put circle A to the right side of this block B. So after understanding the conception of pattern, let's talk about the detailed pipeline of LGMCTS. So at the beginning, we are provided with language description and an image. We use language models and an open vocabulary detector. So the open vocabulary detector is used to parse the image or parse the observation into object categories, colors, and providing them with the different IDs. And this information will be combined with the user's language description. And large language model is responsible for generating a list of patterns and telling us which objects are following these patterns. So after we determine the patterns, we need to convert those patterns into computable distribution. So to do this, to convert the patterns to computable distribution, we define a different parametric distribution function for different type of patterns. And this function should changes based on previous sampled results within the same pattern. So a simple example here, I want to put 4 objects into a line. So at the beginning, the first object can be placed anywhere within this plan. And for the second one, well, technically it can be anywhere, but for computational wise, we require the second one to be within a radius of the first one. And after the first one and second one is determined, the line is determined. So we sample the third one here, and then we sample the fourth one here. So this is how we are transforming a pattern type to a computable distribution function. After we find the distribution function, we actually can solve the whole problem by using a sequentially sampling. But to make this sequential sampling more efficient, we introduce MCTS. So here is, we are using a very classical version of MCTS, where we have 4 different actions: selection, expansion, simulation, and backpropagation. Selection is telling us which node you want to expand, and expand it to generate different actions. Simulation is to simulate how this node will evolving based on different actions, and backpropagation will update the reward. So in the simulation steps, we actually are performing a reachable checking. We will check which object is reachable or not reachable. And we will also check accretion. If I want to do this action, if this action is accretion free, or if this action will be in collision with some other objects. So in either case, we will insert action of moving obstacle away when meet with it. an obstacle in the goal region, or when a target object is not visible. Here we show simple examples here. So we have 4 objects on the table, and the task here is, can you please put the apple behind the spoon, and then also want the cup at the right side of apple. So this problem can be parsed into 2 patterns. One pattern is apple behind spoon, and the other is cup right of apple. So we first sample the position of apple. We say, oh, I want you to be at behind the spoon, so it's somewhere in this region. So I sample this, I sample this region here, say I sample it here. I will find, oh, if I sample this to this region, it's fine. But if I sample this to this region, it's not fine because this cup cannot be put inside this part. So finally, we choose to sample the apple to this region, and then we can sample the apple to this part. To verify the performance of LGMCTS, we propose a new benchmark, ELGR bench. Different from previous benchmark only evaluating the goal configuration, ELGR requests the proposed goal to be executable. So we will call the robots to execute the generated plan, and then checking the final result. Here we show the experiment result. The left side shows the result from the ELGR benchmark, and the right side shows the result from structure-former datasets. We can find from both datasets, our method surpasses all existing baselines by a large margin. And here are some real-world examples. Set all phones into a line. Move bottles into a line and formulate all phones into another line. Move all blocks into a circle while put the white bottle behind one block. Put all boxes into a rectangle and move the white bottle to the right of the one box. Thank you for listening. For more information, please come to our poster sections. Thank you very much.